Here we will discuss about homogeneous nucleation and its mathematical expression. Suppose the temperature of the liquid metal is brought below its melting temperature, such that solid metal is now a stable phase. We can ask the question that, how does the solid appear and the liquid disappear? It would not be appropriate and realistic to assume that such a change occurs all at once by simultaneous cooperative motion of every atom in the liquid phase. In fact, the process of solidification must begin on a very small scale, by forming first a crystalline configuration of perhaps only a few hundred atoms of the liquid, which are called as nuclei. Then the nuclei grow by more and more atoms leaving the liquid metal and joining the crystalline configuration as shown by these three schematic diagrams. The growing crystallites of the solid eventually impinge on one another until all the liquid is solidified. The result is the polycrystalline solid metal. Thus, the process of solidification takes place in two steps, one after the other. First stage is nucleation. It is the formation of small stable particles of solid metal from liquid metal, called nuclei. Second stage is growth. It is the increase in size of these stable nuclei particles by atoms joining them from liquid metal. In the context of solidification, the term nucleation refers to the formation of the first nano-sized crystallites from molten material. For example, as water begins to freeze, nano-sized ice crystals, known as nuclei, form first. In a broader sense, the term nucleation refers to the initial stage of formation of one phase from another phase. Now we will understand this concept through an animation. Thus we can see from this animation that a nucleus is essentially a small group of atoms that have taken up arrangement in definite space lattice, is stable and capable of further growth. The process is called nucleation, and it involves the formation of a new phase within the pre-existing liquid phase. The atoms joined together will be clustered in random shape, but for the sake of calculation we assume that they have formed a spherical shape. Thus, shape of the nucleus formed from the clustered atoms is being assumed as spherical. The figure on the right-hand side shows a nucleus of radius r is formed inside the pool of liquid metal. The volume is 4 by 3 pi r cube and area of this sphere is 4 pi r square. We expect a material to solidify when the liquid is being cooled below its melting temperature, because the free energy associated with the crystalline structure of the solid is then less than the energy of the liquid. This total free energy difference between the solid and the liquid phase is denoted by delta G total. This total free energy is composed of volume free energy, delta GV, and surface free energy, gamma. Thus delta GV is the free energy per unit volume and gamma is the free energy per unit surface area. The magnitude of these terms can be obtained by multiplying them with volume and area. So now we have two free energies. One is associated with volume change as liquid is getting transformed into solid phase, which reduces the volume, and another is associated with surface area. As the solidification grows, the surface area of solid phase increases. Now the question is, what drives this process of solidification? And answer is the volume free energy difference between the solid and the liquid phase is the driving force for solidification. And it is a negative quantity because the free energy of solid phase is less than the liquid phase. Now we will discuss the energy associated with the newly formed surface. You can think that if a solid phase is forming in the liquid phase, this newly formed solid phase will also have a surface area, which continues to grow. And energy associated with it is positive because energy will be required for its growth. Thus, the surface energy of the solid-liquid interface is positive and is denoted by gamma. When we plot the free energy with respect to radius of the nucleus, the green curve on the positive side shows the surface free energy and, being a negative value, the volume free energy is shown by red curve. The total free energy plot is shown by parabolic variation, represented by black color, and the topmost part of the curve represents the value of critical radius r star. In homogeneous nucleation, we frequently use the terms embryo and nucleus. Distinction between these two should be clear to us. Thus an embryo is a tiny particle of solid that forms from the liquid as atoms cluster together. It is unstable and continuously redissolve back into the liquid. And nucleus is the cluster of atoms having size greater than critical radius and is capable of growth. Now let us see that what we can infer from the total free energy curve. When the radius of cluster of atoms forming solid phase is very small, with a radius less than the critical radius for nucleation r star. Further growth causes the total free energy to increase, which can be seen by initial increase in slope of parabolic curve shown by yellow color. And it is not a favorable condition for the growth of solidification. Thus the critical radius r star is the minimum size of a crystal that must be formed by atoms clustering together in the liquid phase, and this nucleus will be stable and will grow further. If the size of clustered atoms is greater than the critical radius, then, further growth causes the total free energy to decrease, which is a favorable condition for solidification. This portion of the curve is shown by green color. This discussion highlights the importance of this total free energy curve. Now we will find out the value of critical radius and critical free energy. At the topmost point of the black parabolic curve, showing the total free energy, the slope is 0. So if we differentiate the total free energy with respect to radius of nucleus, we can equate it to 0. The total free energy will be equal to 0 when the radius will be equal to the value of critical radius denoted here by r star. The simple differentiation of the equation is being shown here, which will give rise to the value of critical radius r star, which is equal to -2 into gamma divided by delta GeV, given by equation number 3. Now we will put the value of critical radius, that is equation 3, in the equation of total free energy given by equation number 1. After putting the values and solving further, we get equation 4, which can be further rearranged to get the value of critical free energy denoted by delta G star, which is equal to 16 pi gamma cubed divided by 3 into delta GV square, and is given by equation 5. Now we will quickly recall the variation of free energy change of liquid and solid phase with temperature. This has already been discussed in the earlier uploaded video of energetics of solidification. Here we have derived the expression delta GV in terms of latent heat of fusion, delta HF, undercooling, delta T, and melting temperature, Tm, shown here by equation 6. Thus now coming back to our derivation, we will put equation 6 in equation 5 and we can write the expression of critical free energy in terms of latent heat of fusion, undercooling, and melting temperature, and is given by equation 7. Thus we have the critical free energy equation having the undercooling term. Now if we put the value of delta GV, defined in terms of undercooling given by equation 6 in the equation number 3, we can find out the value of critical radius r star in terms of undercooling and is given by equation number 8. Now we have expression for the critical free energy and critical radius, the values responsible for continuing the homogeneous nucleation. Thank you for staying at the end of the video.